Hello. Welcome to the U.S. Geological Survey in another installment, of our monthly public lecture series. My name is Leslie Gordon, and it's always my pleasure to introduce, mostly my pleasure to introduce the speaker for this evening. So please welcome. But before I do introduce the speaker, I would like to entice you to come back next month. On April 26th, Kurt Storlazzi, who is one of our geologists in our Santa Cruz office, an oceanographer, geologist, coastal and ocean, is going to be speaking about the role of U.S. coral reefs in coastal protection, how the presence of coral reefs actually helps mitigate any hazards of flooding and wave inundation, storm waves. So please do join us next month to listen to Kurt Storlazzi. I have to slow down. Thank you. So tonight's speaker is Eric Pike. Eric's a physical scientist in the USGS Northern Rocky Mountain Science Center in West Glacier, Montana. So I hope you're enjoying our sunny California weather. At least it's not snowy. He's been studying snow and avalanches, and occasionally some ice, with the USGS since 2007. Eric began his snow and avalanche career first as a professional ski patroller alongside the great avalanche hunters just up the road at Alpine Meadows at Lake Tahoe, California. Eric bounced around between research and the operational world of avalanche forecasting in Montana for a few years. He earned his master's degree in 2009 and is currently working on his PhD, both in snow science at Montana State University in Bozeman. When not working, you might find Eric chasing his two young, energetic sons around the mountains and wondering where all his time goes. So, Eric will be speaking about snow and avalanche science, highlights of applied avalanche research and forecasting. So please join me in welcoming Eric Pike.
Thanks, Leslie, and thanks everyone for being here tonight, taking time out of your evening, this beautiful sunny evening. They told me when I moved from California to Montana that the quality of the snow would make up for the darkness. I'm on the fence still. So again, thanks for being here, and I also want to acknowledge my colleagues in the Northern Rocky Mountain Science Center, particularly Dan Fagery, who is my supervisor and leads our research group, and then everyone there in our research group, and as well as my colleagues and co-authors on the work that I'm going to present tonight. So let's do a little overview first. And what is a snow avalanche? Has anyone here ever actually seen a snow avalanche before? In real life? Sure. Pictures, videos. All right, well, here's another video. And you can see the plume right there. This is in southwest Colorado near Ophir, if you're familiar. And you can see the avalanche fracture across the slope. And it sort of looks like it's really slow moving, but avalanches can travel up to 100 miles an hour. So what we're looking at here is the powder cloud of this avalanche. And you can see it's moving into that forest off to our looker's left side there, likely taking out a few trees maybe. We don't really know about this avalanche, but we're going to talk about how avalanches can have an effect on the landscape in this talk tonight. And they deliver explosives via helicopter on this one, so no one is actually in the starting zone. And they do this because below this avalanche path is a county road and utility infrastructure, so they're trying to protect the county road as well as the infrastructure at the bottom of this road. I'm going to talk a bit about some transportation corridors where avalanches have an effect as well, but in northwest Montana. So again, let's talk a little bit about the fundamentals here. So we need 4 ingredients for an avalanche to occur. We need a sufficiently steep slope, we need a weak layer, a slab above that weak layer, and a trigger. So in terms of slope, you can see on the snow in this building that at the top of the building, it's not steep enough. It's below 30 degrees. Below the building, it's too steep, greater than 50 degrees, but just in the middle is where avalanches like to occur, pretty much between 30 and 45 degrees. When it's too steep, avalanches sort of just, the snow sloughs off, and so we don't necessarily form a slab when it's too steep. If it's not steep enough, and we've seen avalanches below 30 degrees on some slopes, but if it's not steep enough, it's just not enough for the slab to actually move downhill. And so what happens is we form a weak layer. In this case, this is a layer called surface hoar, and it forms on the surface. It's sort of the winter equivalent of dew. Via storm and transport of wind, we have a slab on top, and our skier comes along and is able to trigger an avalanche. And you can see that when that skier comes along and hits just the right spot, perhaps it's a convexity or a rollover on the slope, where the stress is actually concentrated. The added addition of that stress from that skier is too much for that weak layer to hold. So that weak layer collapses. That fracture on that weak layer then moves or propagates across the slope. And so a trigger can be a skier, snowmobiler, snowshoer, or it can be more snow. So our weak layer can sustain a slab to a certain point perhaps. And the weak layer either strengthens or we get an additional load. So let's say it snows again, or let's say we get a bunch of wind, and the wind moves that snow onto that slope and effectively increases the stress on that weak layer. At some point, that weak layer, if it doesn't strengthen, may not be strong enough to hold up that slab, and that's when we get that collapse. So why do we study avalanches? Aside from it's a good excuse to go out into the field and ski around, we study because it is indeed a hazard. Every year, the average number of fatalities in the United States each year is 27. And on an annual basis, that's actually more than earthquakes and any other land slope failure combined. Of course, earthquakes are much more devastating, as many of you know living here. But every year, about 27 fatalities. And it also has an effect on transportation corridors. So in northwest Montana, on the southern edge of Glacier National Park, we have a canyon called John S. Stevens Canyon, named after the railroader who put the railway in. And you can see the red arrow pointing to the railroad just below these avalanche paths. So if my cursor works, and it does, this is our avalanche path right here. Right through the middle between these trees, and it comes right down here. And you can see that they actually built a snow shed a number of years ago to help protect against avalanches. And we'll talk about why snow sheds can be effective and sometimes they can't be. And you also see that the other arrow is pointing to US Highway 2. So it's a major transportation corridor, shipping a variety of products from the Midwest to the coast in Seattle. And we also have, again, the major highway running through it as well. And in the past, they've closed the road due to avalanches and avalanche activity. And the alternatives are hundreds of miles south or going into Canada and going hundreds of miles north. And so you can imagine that it has economic ramifications when they close this section of road. Even though it's a relatively small section, there are pretty big impacts. So we also study avalanches because not only are they a hazard, but they're also a driver of ecological and landscape change. So this is a picture of bulldozers and another machine moving avalanche debris, not only snow, but a bunch of big trees that were basically destroyed and taken out by a large magnitude avalanche in 2009. This is in Glacier National Park along the Going to the Sun Road. So if anyone has been there, likely you traveled it in the summer and there wasn't a whole lot of snow. Certainly not avalanche debris in the middle of the road, hopefully not. And so we'll talk about some of the impacts that avalanches have on the landscape as well. So first we're going to dive into avalanche forecasting. So we at the USGS Northern Rocky Mountain Science Center, and we're in a field station in West Glacier, Montana, northwest Montana. We partner with the National Park Service in Glacier National Park, and we have an avalanche forecasting program for the spring opening of the Going to the Sun Road in the spring. So it's almost time, around first week in April 1st, where they start getting ready and they start moving snow off the road. And it's, as I go to here, it's an 80-kilometer road, and 56 kilometers is closed every winter. So the forecasting program, we use a variety of weather stations, automated weather stations. We actually go into the field, we dig pits in the snow to look at the snow structure, and we help forecast avalanches for the road crew and other park personnel to safely get the road open. So 11 kilometers of the road is actually impacted by avalanches. And there are 37 total avalanche paths. As you can see on the map here, those green polygons indicate or represent avalanche paths that cross the road. So on the image on the right, you can actually see the road as it crosses through right here. it crosses through the middle of some of these avalanche paths. So in this case, the road isn't necessarily just at the bottom. So we're not just forecasting for big avalanches that have a probability of reaching the road. We're actually forecasting for avalanche, even small avalanches that might cross the road when the road crosses through in the upper part of the avalanche path. So again, it's a vital artery of visitation, particularly in the summer. And that also in and of itself has economic ramifications when it's not open for the local surrounding community, but region-wide as well. So the avalanche path starting zones along the going to the sun road, the starting zones are where the avalanche starts, right? And that's about 500 to 3,000 feet above the road level. So you can imagine that 3,000 feet above the road, often conditions can be very different. So it may feel like spring down on the road at, say, 4,500 feet, but at 7,500 feet or 8,000 above well above the road, right up here in this zone, can be very different, particularly the snowpack itself. So while down here it might resemble more of a spring snowpack, up here it can still be a wintry snowpack with quite a lot of variability. So a little historical look at some of the avalanches along the going to the sun road. In 1953, 2 machine operators were actually killed. 3 were caught and 2 were killed in a wet snow avalanche that that released in an area called Alps 1 Avalanche Path. And you can see the debris here and folks actually trying to dig through. And that was a pretty destructive avalanche, of course. In 1964, a bulldozer was knocked off the road in an area called the Big Drift. And this is pretty much right at Logan Pass, which is right on the Continental Divide. So this is actually just on the east side. But you can see over here, this is the crown of the avalanche where we're looking at about 12 to 15 feet of snow that had released. So as this bulldozer was moving through, it actually triggered the avalanche itself and then was knocked off the road. And the most recent was in 2005, which was a close call. Fortunately, no one was injured, but a similar situation where the bulldozer was moving snow, pushing snow off the road, triggered an avalanche. It broke right next to, or right at the bulldozer, and the bulldozer went over the road. Fortunately, he was a very skilled operator. He was able to put the blade down and didn't roll the machine or didn't go that far, and they were able to pull it back up in a couple days. So, as I mentioned earlier, we have this partnership with the Park Service, and we, as USGS researchers, we try to figure out how can we make forecasting better so that we're keeping people safe. And the biggest problem that the road crew faces and that people traveling along the road in the spring face is wet snow, right? We're moving into the spring, so we're not dealing so much with dry snow avalanches, though we do when it does storm. We're really focused on the wet snow avalanche research. So let's talk a little bit about what wet snow actually is. And there's 3 main types of wet snow avalanches. We have wet loose avalanches, wet slab, and glide avalanches. So wet loose avalanche, as you can see from the image here, these avalanches involve really just the surface snow, so anywhere from the top few inches to maybe a foot at most. But what happens is they start at a point, and then they tend to fan out, as you can see, like in an upside-down V pattern. And in this case, sun shining on these, this is a southerly or southwest-facing aspect, so we have a lot of sun hitting this slope. It's warming up the rocks, and you can see that all of these avalanches in this image started near these rocks. So we have a lot of short-wave radiation being absorbed by the rocks, heating up the snow adjacent to it, and that's where we're going to get these wet loose avalanches. So what happens is, as the sun and warm temperatures heat up the snow on the surface, it reduces the strength, it reduces the bonds in between each little snow grain, and then it reduces its strength, and it releases and goes downhill, because that's what snow ultimately wants to do. And before I go to this one, the wet loose avalanche, they're relatively predictable. We can say that it's going to be warm and sunny, and we're probably going to see wet loose avalanches. Wet slab avalanche, like in this image, is definitely harder to predict. And this is a really large avalanche. As you can see, this is the crown right over here. Starts up here and comes all the way down and around. And what happens here is, as I mentioned before, in a dry slab avalanche, we have avalanches occurring because the weak layer can't hold the slab above. Well, that's the same in a wet slab avalanche, but instead of adding more stress or a load to the slab, we're actually decreasing the strength of the weak layer in a wet slab scenario. So in the schematic here on the right, as water moves through the snowpack, whether it's melting or whether it's rain on snow, it moves through the snowpack via flow fingers. Water will move through the snowpack any way it can, the least resistant path. And it'll eventually hit potentially an interface between the slab and if we have a weak layer in the snowpack. And with fine grains over coarse grains, what it tends to do is pool along that interface. When it does that, it decreases the strength of that weak layer, and it's not able to support the slab above. So that's a wet slab avalanche. And a glide avalanche, we sort of call these the circus oddity of the avalanche world because they're really hard to forecast. So as I mentioned, snow likes to move downhill. Gravity likes to do its thing. And it moves downhill at variable rates, and we call that glide. So as the snowpack moves downhill at variable rates, we tend to get a tensile crack that forms. And so here we have what we call a glide crack or tensile crack, and you can see sort of in this area and all the way around the snow actually buckling. And what can happen here is when we get a glide crack, often we'll get a glide avalanche, but not always. But what we need is free water at that ground snow interface. So as water moves through the snowpack, it then pools at the bottom of the snowpack and the ground interface. And it basically lubricates that interface right there so that the snowpack will then start to glide downhill even more. And it also requires relatively minimal surface roughness. So if we look at this image, and you can see these are glide cracks, one's right here, over here, another one here, up here. You can see that they're all on rock slabs. So you can imagine that as the water moves through that snow or that slab, when it hits the rock slab and the snow interface, it's not like soil where it can actually move into the soil. It actually hits the rock. It's got nowhere to go. So it's going to move along that interface. So we tend to see glide avalanches occurring on smooth rock slabs and in the same location every year, which we'll get into in just a little bit here. So we want to start at the beginning. What's actually causing these wet snow avalanches to occur? So we looked at wet slab and glide avalanches because, we have a pretty good handle on what happens with wet loose avalanches. And so we looked at, on the right is the results of what we call a classification tree. And we looked at avalanche days versus non-avalanche days. We looked at the 60 variables of weather and snowpack to basically determine what are the most important variables or what are the discriminatory variables between an avalanche day and a non-avalanche day. And so what we found out is that the first node here, avalanche days, non-avalanche days will split, and avalanche days we get with maximum air temperature. And as we move down, again, non-avalanche and avalanche days, the non-avalanche days that were left are split again on mean air temperature. And then the final node right here splits on a change in snow depth over a period of 5 days. So what this tells us is that, one, air temperature is important, and two, the settlement in the snowpack seems to be an important variable as well. And so this is really important because as we see increasing air temperatures, particularly creeping into late winter, we may begin to see more wet snow avalanches. So it becomes even more important to try and understand these wet snow phenomena. So as I mentioned, these glide avalanches tend to occur in the same location every year in areas that affect the road transportation corridors. We call these repeat offenders. And these repeat offenders, we wanted to figure out, why are they occurring in the same spot each time? So we looked at, again, a number of variables, but this time terrain variables. So slope, curvature of the slope, substrate underneath. We were looking at smooth rock slabs versus, say, areas with a lot of vegetation underneath. And what we were able to find is that, of course, as I just pointed out, that the areas with smooth rock slab are areas where we tend to see a lot of glide avalanches. So we modeled this across Glacier National Park. The red polygons indicate areas of known glide avalanche activity, and the blue indicate modeled areas. And so we can see that there's a fair amount of area that has the potential to harbor glide avalanches. And we also use time-lapse photography to get a handle on when these things are actually occurring because we're not out there 24 hours a day. And of course, we can't capture it at night because it's dark. But we can see here, just as an example, where the red box highlights, you can see 2 days later we have what appears to be a small avalanche. It's actually about 200 to 300 feet in width, but we're pretty far away, or the camera is relatively far away. It's actually about 7 to 8 kilometers away. And then, even 2 days later, we have another small glide avalanche right here. And you can see the glide crack begin to form right back here. And then in just 1 hour, we have a really massive glide avalanche that occurred in this basin right here. So again, time-lapse photography provides us a nice way to be able to capture these events when we're not out there and when we can't see them in person. So let's shift a little bit from avalanche forecasting, and we're going to talk more about tree rings and avalanche ecology and how we can use tree rings to actually develop an avalanche chronology. So dendrochronology, if anyone here or online is familiar, it's the study of tree rings. And so we can actually use tree rings, people use tree rings to sort of study how big of a snow year it was, right? We get big tree rings sometimes. Or if we're in a drought, we'll have often really thin tree rings. So we can use these tree rings and count them by actually looking at avalanches. When they hit a tree, will leave a signal. And I'll get into that signal in just a second. But first, let's talk a little bit about the avalanche path morphology, because this is important. As I mentioned before, the starting zone is where avalanches tend to occur. Avalanche will release in the starting zone and move down this track. And then it'll eventually deposit debris in the runout or the deposition zone, all the way down here at the bottom. And so this is an image of the avalanche path that I showed earlier, where the bulldozers were moving a lot of debris. This is in Glacier Park, and this is the image. This is an actual image taken after that large magnitude event. So all this brown color you see here is actually vegetation and debris, trees knocked over and transported in this large magnitude event. A lot of these trees were actually carried from way up here. So right here by this little nick point, this was actually forested. And it increased the avalanche path. This large magnitude event increased the avalanche path by about 30% in width. So you can see here that this track is, in this particular avalanche path, is relatively low angled. It's about 15 to 20 degrees. And most avalanches, if they're small or maybe even medium in size, will begin in the starting zone and typically end up right around here. So from this starting zone, to give you a sense of scale, all the way to the runout zone is about 4,000 vertical feet. And so to begin an avalanche beginning way up here, to cross a track that's relatively low angled, and then to take out a lot of trees and end up all the way 4,000 feet below in the riparian zone or in the valley bottom, is a really big avalanche. And so we'll talk a little bit more about that one in just a sec. But getting back to tree rings, they're kind of the fingerprint of avalanche activity. And you can see here that this sort of shape right here and this shape of the tree, this would be the uphill side of the tree before it was knocked over. So when an avalanche comes down, hits a tree, it'll impact that tree, and it actually, not always, but often leave a scar on the tree ring. So here, in this blue arrow, is pointing to a scar from 1993. This one is a little scar, but more of what we call reaction wood. And this one over here is, again, a little bit more of reaction wood. And so there is a signal that it leaves, and sometimes it's a really good signal, like a big scar, and oftentimes it's a little more subtle. So for this project, we actually are in Glacier National Park, but also in the surrounding adjacent mountain ranges. So we're looking at 4 mountain ranges here. The red dots indicate our sample sites. So we collected over 600 samples, these cross sections from trees, so that we can actually look at the tree rings. And a quick little overview: 2 of our sites again are in John S. Stevens Canyon. The blue polygons are the avalanche paths, and then again the map that I showed earlier, just in a different color, of the avalanche paths that affect the going of the sun road. So here's a little video about what we actually do in the field. Yep. And let me see if I can plug it in. I forgot to plug in the audio here, but we'll continue on. Basically what's happening, and I'll let it run, is we're looking for scars on the tree. And so in this case, right here, we suspect that that's a scar or that hit the tree. And what we'll then do is cut into the tree. We want to get a cross-section from this tree, and so we take out this cross-section. We could core these trees, but they're dead and downed, so it's okay to take a cross-section from these trees. But often what happens if we just get a core from this tree, we're not able to, we might miss the signal. And so, depending on where we core, even if we core in all 4 or more directions, that's a lot of cores, but some of these scars are really small. And so we might actually miss it, even if we go in where the scar is, on the outside, the exterior of the tree. But again, not all trees are going to show a scar on the exterior. So maybe a really big avalanche hit in, say, 1950. And for instance, let's look here. We have avalanche scars from 72, 85, and 93 on this 83 or 82-year-old tree. So an avalanche came in and hit this side, and then it looks like it also came in and hit this side. So we sort of have the tree rings growing around that scar, around that disturbance. But imagine that maybe this wasn't here, and we didn't know where the scar was on the exterior, and we might have missed, by coring, we might have missed a smaller scar that exists further in. So having these cross-sections, while it is a lot of work because we actually have to sand them down and make them really smooth, because often you can't see these scars until that cross-section is quite smooth, and then they pop out. And so, for instance, here's one where in 2003 we had an impact scar. And as I mentioned before, there's a degree of signal. And in 1959, we have something what we call reaction wood. So we might not necessarily have a really obvious scar. But when it gets hit by a tree on the uphill side, the tree, it counteracts that and buffers that by growing more wood on the downhill side. We call that compression wood. Or if the rings are really small, we call that reaction wood. So if we don't necessarily get a scar, we have other things to sort of fall back on. So not only are we able to build a chronology over time, looking at sort of the magnitude of avalanches over time, but we're able to, when we collect trees in place, we're able to develop a return period frequency map. So this is near the railway this is the railway in the US Highway 2 corridor. This black rectangle here is a snow shed. And what we're able to do then, again with our in-place samples, is we're actually able to look and develop a return period frequency. So that you can see down here, obviously avalanches will reach the railway grade or the road much less frequently as they do further up in the path. Up here it's anywhere on the scale from about 2.5 to 4 years, whereas closer to the snow shed, we're looking at about a 6 to 10 year return frequency there. So these are just 3 avalanche paths along the Going to the Sun Road, but it gives you a bit of a sense of how old our avalanche paths are. The problem with studying trees in an avalanche path is the avalanche likes to take out the trees. And they're not always there, sitting there nice at the bottom of the avalanche path or in place for us to just sample. And so we have regeneration of these forests, and a lot of these trees are young. So sometimes it's hard to get a chronology that goes back very far. Fortunately, so far we have a decent chronology, and in this case you can see this is the number of responses actually. So this isn't the number of samples. We're looking at avalanche responses in these samples. And we actually have responses that go back to the late 1700s, which in an avalanche chronology is pretty far back. The folks who study other proxies may not think so, but for an avalanche path, that's actually pretty far back. So what we've done here, as you can see, there are more responses in recent years, and that makes sense. There are more trees. So in order to normalize it or to scale for it, we actually take the number of responses per the number of trees actually alive in that year. And so we then have a threshold percentage that we use to say, well, this is likely an avalanche year. So aside from developing a chronology and a return period frequency, avalanches also have an impact on the landscape. So you can see from these repeat photos in 1997 to 2004, the number of trees, of course, is markedly different. But one thing to notice over here is that there are a fair number of trees, but then over on this image in 2004, there aren't. And you can see that now, in a large event, we could potentially have an avalanche that comes down, and if it's the whole width from what we call the trim line over here to the trim line over here, if it's the whole width of this avalanche path, it's going to come down and potentially reach the rail grade on the side of the snow shed. So as I mentioned earlier, snow sheds can be very effective, but when we have a changing landscape like this, they're not necessarily 100% effective from guarding against avalanches. So in this case, we also have a interaction with wildfires, where wildfires, if they burn the forest, they open up potentially more avalanche terrain. Trees act as not only an anchor in the snowpack, but they can also act as surface roughness. When an avalanche comes down the slope and it hits a bunch of trees, it can actually, the trees help slow the velocity of that of the avalanche. But when there aren't any, because they've been taken out by an already large avalanche, it makes the probability of an avalanche reaching further down even greater. So you can see the difference in landscape change and how that might affect the the avalanche regime. And again, looking at return period frequencies, this is just another illustration where these are all down trees from an avalanche. So when we take out these down trees from a large avalanche, perhaps what was maybe a 2.5 to 5 year return period frequency up here is now perhaps down here, and perhaps the 10-year now becomes even further down. So by developing an avalanche chronology, one of our goals in this study, and we're in the process of this work right now, is to actually associate some of these large magnitude event years with weather and climate drivers. So looking at things like storminess or upper level air pressure indices, and potentially other teleconnection indices as well. And what's sort of noteworthy about this cycle, and this was the cycle in 2009 that I previously mentioned, is in early January we had relatively cold temperatures, minus 15 degrees C, and we had a pretty sharp increase in air temperature to near freezing, and this is at about 7,500 feet. 7,500 feet in northwest Montana is pretty much the alpine, so it's right at the upper level of subalpine and right getting into the alpine terrain. And so that for us is a pretty high snow level. It's pretty similar to here in the Sierra as well, or if you get snow levels at like 8,000 feet, that would be fairly comparable. Or at least in the Tahoe region. In the High Sierra, it's a bit different, of course. But you can also see that during this cycle, we had a sharp increase in precipitation as well. And so it rained at the low and mid elevations and even a little bit into the upper elevations. So what we had is a lot of rain on snow and a potential wet slab scenario. But then we also had really heavy wet snow up high, sort of acting as a dry slab scenario. So we have sort of the combination of both wet slab and dry slab in the same avalanche. And on the image on the left is actually from a different avalanche, but it's from a wet slab avalanche, and you can see that the debris that it can deposit is pretty substantial. So in that 2009 avalanche, the image on the left shows the debris pile left along the lower part of the Going to the Sun Road, again about 4,000 feet below. And the image is foreshortened there, but that debris pile is about 30 feet deep, and that person is definitely not 10 feet, so it's a little foreshortened. But then on the upper part of the road, it actually damaged a part of the road, so it took them a while to repair that. That's summer. All right, so another project we're working on is snow depth mapping. And we want to know the not only variability of snow depth across an avalanche path starting zone, but we also want to get a sense of how much it's changing over time. So when we get a storm, we have automated weather stations that sort of give us an idea of how much it snowed. But then when we have wind events that tend to load snow from perhaps the leeward or the windward side, or the windward side of the ridge, loading the leeward side, what we do is basically make a good educated guess about how much new snow has been transported. So we might say, well, we had winds for 6 hours in the 30 mile per hour range, and now we have a slab that's about maybe a foot in addition to what we already had. So what we're trying to do is get a better sense of how much things are actually changing. So we're using drones or unmanned aerial systems and a photogrammetry technique called structure from motion. And we're basically flying over these starting zones and mapping them, and I'll explain how we can do that. But first, structure from motion is a photogrammetry technique where you take in the middle here, our scene that we want to image and map. And in our case, we don't need to map the back of the avalanche path or the back of the mountain, so we just do about a 180 around it. And what that allows us to do is get overlapping images of our scene of interest. And the objective is to detect change in snow depth through time so that we can create these high-resolution products where we can actually look at a change in snow depth from, say, 1 week to another week, or even just a few days if we have a storm or a big wind event. So we take our drone out, and we just have a small quadcopter, and we're able to attach our camera to the bottom of this, and it's a 15 to 20 megapixel camera, depending on which one we're using. And we're actually able, in this case, we are mapping the open area to the right over there. And while it doesn't look like your classic avalanche path, it is avalanche terrain. It's sufficiently steep, but it's a little more forested. So we wanted to get a sense, we have a pretty good sense that we can capture it in this open terrain, the snow depth change, but we wanted to look at, are we able to capture it in more forested or subalpine terrain? So here you can see in the bottom right where those two green markers are, is where we launch and land, and the yellow lines indicate our flight paths. And so this is just a small screenshot of when we plan our missions in the office before we go out and actually fly. We want to be sure that, one, we're well above the ground, so we use a digital elevation model, but we also have to account for trees that are out there as well. So we have to plan it pretty carefully, and we take a cross section, or a upslope and downslope, and then a cross slope transect as well. And we're limited by our battery power on this particular drone, and it's a quadcopter, so our battery life is about 12 minutes. So we'll typically fly an upslope and downslope transects, bring it back, and then send it back out again after we swap our batteries. So if we go out and we just try and map this, that's great. We have an idea of what we think, or what shows how much snow depth is and the variability. But we actually need to go out and make sure and verify that that's the case, particularly now. So we go out and we do snow depth manual measurements. Again, we don't want to necessarily put ourselves in the starting zones here. So what we tend to do is walk around on the safe ridges around our avalanche path, and that's still within our scene that we're interested in, and so we're able to verify these snow depths by probing and taking manual measurements. We also have to place ground control points out there so that when we take our images, that they need to be visible in a number of our photographs. And so we spray paint these X's on the snow, and we take manual measurements there too, but we get high resolution GPS and GNSS points so that we're able to actually geo-reference our images and our maps, of course, once we bring it back into the office and do all of our processing so that it's even more accurate. So going out in the field is really fun. That's the fun part. That's why we do the work. But the processing, of course, is what takes the longest. And the nice thing, though, is that we put all the time in by processing, and let our computers do a bunch of the work and let it run overnight. And we're able to create these really cool and high-resolution products. This is a dense point cloud. So if anybody is familiar with LiDAR, you fly over an area, and LiDAR basically the sensor shoots a laser down, and it gives you a return pulse, and it gives you a bunch of points. And you can then get a bare earth digital elevation model with LiDAR. Structure for motion works similarly. As I mentioned, we take these overlapping images. And so what it does is it takes the common or tie points in those overlapping images, and you can imagine that sort of propagates through every image as you have these common points. So in this dense point cloud, we have about 50 million points. And it's a relatively small slope, even though it is an avalanche terrain. The vertical relief here is about 500 feet, so it's not quite that large. But 50 million points is when processing can be fairly large. And so the difference with structure for motion is that when LiDAR moves through, it can actually move through gaps, in trees, and it'll create a bare earth model for you. Structure for motion isn't able to actually move through. It's not sending a pulse down. It's using these tie points. So we can't create a bare earth elevation model, but we can create a digital surface model. And so here we've created a 3D model, and it's really low resolution. The high resolution one that we created would have crashed the presentation, so I didn't want to put it in here. But the 3D models are nice. They're pretty to look at. They're good for outreach and presentations. But really, it's the digital surface model that we're interested in. And you can see this is a digital surface model with an accuracy of about 4.9 centimeters. And so it's good enough that you can actually see right here, you can see our ski tracks. And we made nice, pretty figure eights coming down. And over here, you can see sort of our up track where we skinned up to take our manual measurements. And down here on the far right, you can actually see our vehicle. So this is important because with a 5 centimeter accuracy in both the X and Y and even the vertical realm, we can actually detect change on a really small scale. So yeah, we're going to be able to detect change when it snows 2 to 3 feet, but we can hopefully also detect this change when we have storms or wind events that are around a foot or maybe even a little less than that. So what we then do is take our digital surface models or our point clouds that I showed earlier, and we basically take the difference between the two. It's a simple subtraction of those points in the point cloud or the pixels in your digital surface model, and that allows us to get our change. And again, this is a great tool because now we're able to launch from all the way down here, not necessarily put ourselves in a hazardous position, but we're able to map a really big area and look at the variability across that area as well. And that helps with, forecasting for, okay, we got a wind event, so how much more of a slab did we put on top of that weak layer, if there is one, or how much new snow did we get? Another nice product that another byproduct is we're able to map these avalanche crowns. And so this is a digital surface model that was created last spring. And you can see here this arrow points to an avalanche crown right here. And the accuracy of this digital surface model is about 13 centimeters. And it captured a small one over here as well. So in real life, this is what it looks like. This is the avalanche crown that we were able to capture, and then this is the small one over there. So any guesses as to the height of the crown of this avalanche right here? No guesses? 30 feet? That was a guess. Higher? Much higher. In the last talk, we got a range from 2 meters to 200 meters, so somewhere in between there. So yeah, around here it's about 15 to 20 feet, and then over here at its farthest edge, where this crown is, it's upwards of 60 feet. So that's a big, that's the whole snowpack. We're looking at a glide avalanche right here. And, this is an incredibly deep snowpack because what's happening is over the course of the winter, and this is in the spring, but over the course of the winter, we have, of course, storms falling, but then we have wind loading from sort of the back of this image as wind transports snow, and it just basically deposits all that snow right down here. And we also have avalanches that occur up here and put all their debris down here as well. And so it's an incredibly deep snowpack over here. But this tool allows us, because this is quite far away, this tool allows us to actually capture how large these avalanche crowns are. And when it goes to the ground, that's obvious. But when we're working with crowns that aren't necessarily at the ground, it gives us an idea of what layer they actually released on. All right, so to finish up here, our next steps is our research is going to continue to be driven by operational or management decision making. So we're there to basically help. In this case, on the transportation corridors, we're there to help keep people safe. We're going to continue to refine our wet snow models. So, we used a number of variables as inputs, but we also want to continue down that road and make sure that the variables we put in and what's coming out still works, and we're using that operationally to some extent as a guidance as well. And then this spring, as if it ever melts in Montana, it's been a big year, a big snow year. But when it does melt, we're going to continue to explore and map our snow depths across these starting zones, not only in periods of accumulation, but also melt. So look at how rapidly the snowpack is settling, because as we learned before, that was one of our important variables for our wet slab avalanches. So thanks for attending, and any questions?
Thank you, Eric. And I'm sure many of you have questions, and many of you have been here every time, so you know the routine. You're first in line. We have 2 microphones set up in the 2 aisles. Please, if you are able, get up and use the microphone so that we can all hear you. If for some reason you're not able to get up to the microphone, wave at me, and I'll come and bring you one. So why don't you go ahead, sir, with the first question.
Thank you for the presentation. I had a question about preempting these avalanches through blasts, the way they do on ski slopes. So if you knew that, say, the BNSF railroad was in the path, could you potentially preempt that or trigger that avalanche before? And if so, if not, why not?
Yeah,
thank you.
That's a great question. I should have elaborated on that one. So yes, obviously, using explosives is a great mitigation tool. There's a couple of things there. Is one, you can close the road and the railway for a short period of time, and deliver the explosives in a variety of techniques, and again, create the avalanche on your terms when you want it to go down. One of the issues, and they do that along the railway on emergency purposes. So if it's a really big storm and avalanches are imminent, they've already seen smaller avalanche activity. But one of the issues is that the starting zones are in Glacier National Park, which is a wilderness area. And so they did an entire environmental impact, or environmental assessment, and it was deemed that they weren't going to allow avalanche mitigation via explosives on a regular basis and only in emergency conditions. So that's the reason now that that they don't do it regularly, because you're right. If you basically in every storm, even if it's a small storm, you basically mitigated through explosive mitigation, then you could knock down smaller avalanches and potentially have less less of an effect. But because the starting zones are in the park, that's what they decided.
Hi. I'd be interested to hear anything more you might say about how global warming is affecting your work.
Yeah. So that's a great question that I actually get quite often, and it's one of the questions that we're working on. So obviously, global air temperatures are increasing, and as I sort of alluded to, we might see more wet snow avalanches creep into late spring, and perhaps even more rain on snow events midwinter. Especially here in the Sierra. I mean, we're used to rain on snow events, and in the Cascades, but those coastal regions. But now, we may begin to see, and I say may because at least in the U.S. there hasn't been any definitive work. So that's part of what we want to try and look at with the tree ring work, is to see, we can't necessarily tease out, rain on snow events midwinter, but we can sort of determine, at least on a shorter scale, where we have weather records that, automated weather stations that sort of show that. In just north in British Columbia, north of us, near Rogers Pass, they looked at some of this, and they found that there is a slight increase in midwinter rain on snow events, and their observational record goes back a lot further, to the 1940s or 50s. And then in the Alps, they've shown that there has been no change. But again, observational records can be pretty scarce and hard to come by as we go further back in time. So that's why we're trying to use tree rings as a proxy there.
I had a question. I was wondering if drones would have any role in delivering explosives and how does your work compare with what's going on in Europe? Because they've built things in the path of well, we've got a head start because we haven't built in front of these things as much. But
yeah, exactly.
I was wondering how this work compares to what's going on over there.
Yeah. So the first question of delivering explosives via drones, I actually read something a few months ago about a company that proposed to do that. They were trying to do it outside of Telluride in Colorado. I haven't heard anything since, and it's doable as long as the payload, of course, on the drone is. Or as long as the drone has a pretty high payload, and depending on what sort of explosive if it's a 2-pound charge that a lot of ski areas use, just a stick of explosive, then that's certainly doable. But other than that, I haven't heard, and it might be. And in terms of the work that we're doing, comparable to Europe, in that case, I mean, they have, they've been living and working and dealing with avalanches and avalanche terrain all the time, or for a long time. And they have a variety of techniques that they use to mitigate avalanches, from explosives to, they basically will build structures in the starting zones to disrupt the snowpack so that weak layer can't form, or can't form widespread across the slope. So they'll use snow fencing. They also have avalanche dams, like for instance in Innsbruck in Austria. They have avalanche paths that come all the way down into town, but they have these really big diversion dams. Sort of higher up, of course, so that when an avalanche comes down, it's diverted, and so you don't have the concentration of impact, and it sort of disperses that impact. So they and in Colorado too, there's a lot of work being done there in terms of building structures that help mitigate, and also explosive delivery, remote explosive delivery too, not just throwing charges.
That was kind of the basis of my question, is that you could get access, quickly into areas that people wouldn't want to, you just wouldn't get into normally.
Yeah.
Around wild areas.
Yeah, exactly.
It seems to me this is similar to fracture in brittle materials.
Yep.
And I wonder if you're using the methodology of fracture mechanics to look at stress intensity and critical flaw size and all that sort of thing.
Yeah. Yes.
Yeah.
I'll explain more than that. So let me caveat that with I am not an engineer. But yeah, a lot of folks, particularly again in Switzerland and folks out of Bozeman, have used fracture mechanics to look at fracture within the weak layer. So one of the things, and it was actually a really cool test we use when we dig snow pits. We do something called a stability test. So you can basically isolate a column, and previously we would just isolate a 30 centimeter by 30 centimeter column, so 1 foot by 1 foot. And we'd take our shovel, our avalanche shovel, and set it on the top, and you sort of tap on it to apply your stress, right? And so you're looking to see if that weak layer or any layer in the snowpack breaks. So about 10 or 12 years ago, sort of using mixed mode propagation, where we're not just looking we're not looking at shear, we're also looking at collapse. And so what they found is if you take a block now 30 centimeters back but 90 centimeters wide, we can actually look at not just the fracture part of that equation, but also propagation. And that's really what we want to know. It might break, but is it actually going to propagate across? So again, we're using a small block that may or may not be representative. It's just a small point, especially with spatial variability. But it gives us a better idea of how likely is that weak layer to not just fracture, but also propagate. So yeah, those guys have been doing a lot of work with fracture mechanics.
Thank you. I was curious why you chose the photography over LiDAR.
So the right now we actually have LiDAR have flown LiDAR along the entire canyon. That was in the summer, so we have a reference digital model that we can use. Problem with we want to sample in a relatively short time scale, so we're talking maybe every week or every couple weeks or even more frequent than that. To be able to typically LiDAR is flown from a fixed wing aircraft, and so as it's flying over, just to get it in the air is incredibly expensive, and then to process all of those data are really expensive as well. So the bottom line there is that it is cost prohibitive. If you're sampling a large area, it's well worth it, but the frequency that we want to sample, it's just not economically or fiscally responsible.
Not until the instruments are like pint size, right?
Exactly, yeah. So we've looked into, are there small LiDAR units available to put on these drones? And I think folks are in the process of trying to develop them. And actually, there are small LiDAR units, but they're just not that great right now in terms of the accuracy that we want. So right now, we're just plunking down a camera and using that, and it works really well so far.
Thank you.
Yeah, thanks. One more.
Here's a fun question.
Uh-oh.
Have you ever been in an avalanche? Actually surf out of an avalanche?
Yeah, so the first part of that question is, unfortunately, I have been. And it was, thankfully, well, maybe I shouldn't say that, but it's been twice, and they were small avalanches. It was early in my career. So they were relatively small, and I wasn't buried, which is good, and they were... I like to think that I chose these sort of small, low-consequence slopes, and that's where I was testing things. And it was actually during when I was conducting a stability test, and it was just right after that. So, but again, they were really small slopes. So, can you surf out on an avalanche? It really depends. Sometimes a lot of it depends on the debris flow, and within, again, the past 10 to 15 years, there's been a development in technology called a balloon pack or an airbag pack. And so you basically have a backpack on and it has a little ripcord. And it's powered by either a fan or a gas cylinder. And you can pull this ripcord and you basically have a big balloon, a big airbag basically, that blows up right about around your head. So you have this big balloon around your head. And the theory there being is that these, sort of like the Brazil nut effect, you have these, the Brazil nuts always end up on the top in your mixed nuts canister, and so you basically get basically pushed to the surface as you get mangled through the avalanche debris. So, if you're not injured or if you don't die by trauma, then they do help with survival rates, and they're not the silver bullet by any means. People have been fully buried while still wearing an avalanche balloon pack. Or an airbag pack, and so They're not a silver bullet, but they do help. If you don't have one, the advice from sort of age-old avalanche hunters is that you just gotta, if you're caught in one, you fight, and you just try and fight it, just stay near the surface. And again, that's much easier said than done. And yeah, they're really powerful things.
Any other questions tonight for Eric about snow avalanches? Well, I want to thank you all for coming and joining us. And especially I want to thank Eric Pike for such an enlightening talk. Thank you.
Thanks, everyone. I appreciate it.